Electrochemical thermodynamics gives the reason why and which direction an electrochemical reaction can occur, and therefore in the very first lecture I would like to introduce this very fundamental aspect. And we start with the general difference between electrochemistry and chemistry to introduce the most important concept of electrode potential. And then in the second bit I discuss the origin of electrode potentials and then mathematically describe it. Finally, we come to the general electrochemical thermodynamics based on electrode potentials. And I would also like to present some useful additional notes of distinguishing electrochemical potentials, interfacial potential differences, and electrode potentials, which will be mentioned in the content above, and also distinguishing various electrode potentials in case you are still confused and need further elaboration. To understand the origin of any electrochemical reaction, we need to first ask a question: what is so special about electrochemistry as compared to chemistry, or more precisely, general redox chemistry? Well, fundamental electrochemistry focuses electron transfer between an electrode and a electroactive species in the solution, and it could be a molecule in the solution, and the electron transfer may be in this direction. Whereas in general redox chemistry we focus on electron transfer between two molecule species. One is A, one is B, and we have electron transfer. So one is more reducing, the other is more oxidizing, and after electron transfer they may both form new species and become more stable. And therefore we can write the equation as A plus B gives C plus D. Then how do we know whether a chemical reaction would occur, and if yes, to which direction it would go? Well, thermodynamics predicts that a spontaneous chemical reaction always occurs in the direction of decreasing Gibbs energy and a constant pressure and temperature. To describe that, we plot Gibbs energy of the system as a function of extent of reaction psi, and at leftmost we have all the reactant molecules, and rightmost corresponds to all the product molecules. And the typical Gibbs energy curve would look like such a parabola. And according to the criteria of reaction spontaneity, we have mathematically the change in the Gibbs energy of the reaction system smaller than 0. But for discussing some dynamic processes with the formulated reaction, we also need to take into account the direction of reaction by involving the extent of reaction. Therefore, we define the reaction Gibbs energy as the derivative of the change in the Gibbs energy of the system with respect to the extent of reaction and the constant pressure and temperature. And actually we can see that reaction Gibbs energy is basically the slope of the energy curve. Then we consider three thermodynamic processes. First, initially in this solution there's only reactants, and then it changes to all the products. And if we connect these 2 points, the slope is negative, and therefore the reaction Gibbs energy is smaller than 0, and forward process thermodynamically favored, therefore there will be more product molecules reproducing. And second, in the reaction mixture there's only product molecules, and it goes to the reaction system with the lowest energy state. And in this case the reaction Gibbs energy is bigger than 0, and therefore backward reaction is thermodynamically favored, and there would be more reactant molecules producing. And third, there's a special case where the initial state of the reaction mixture is already at the lowest energy. So in this case, the reaction Gibbs energy is equal to 0, which means there's no net reactions, and the reaction is in equilibrium. So from the above, we can see that by knowing reaction Gibbs energy, we could judge whether or to which direction the reaction would occur spontaneously. But further, we want to quantitatively understand this tendency by relating Gibbs energy to the properties of each species. So we introduce the concept of chemical potential, which is mu I, the chemical potential of species mu, equals to the change in the Gibbs energy formation with respect to its amount and the constant temperature and pressure and the amount of all the other species. So we can also understand the chemical potential as partial molar Gibbs energy, and this term is specific to each species. Then we look at the Gibbs energy change of the whole system would equal to the change in the Gibbs energy formation of all the reactants and all the products. Combining these two equations, we have the sum of the product of chemical potential of each species times the change in their amount. And then the change in the amount of C and D must be opposite to A and B. So we have the minus sign for A and B and positive sign for C and D. Then if we divide both sides of the equation by delta psi, we have this term actually equals to reaction Gibbs energy equals to mu C plus mu D minus mu A minus mu B. And therefore, from this final equation, we could see the reaction Gibbs energy or the tendency for electron transfer completely depends on the relative magnitude of the chemical potential of each species. After refreshing the memory of general chemical thermodynamics, we can then turn to the more complicated case of electrochemistry. As seen from the description at the beginning, the special feature of an electrochemical reaction, in contrast to other types of chemical reactions, is the involvement of electrode phases. Therefore, we use electrode potential instead of chemical potential to quantify the tendency of an electrochemical electron transfer. And I will give you two quick examples to show the usefulness of electrode potential. One is fluorine is reduced to fluoride, and the other is lithium ion reduced to lithium metal, and the electrode potential is 2.87 volt and minus 3.04 volt. Actually, both examples are pretty extreme. They have very large absolute values, and there's a huge difference between these two electrode potential. Now, just from this particular electrochemical point of view, an electrochemist can know that fluorine is a strong oxidizing agent, whereas lithium is a strong reducing agent. So that in the following two sections, I will focus on discussion of this very important concept of electrode potential, and I will start with the origin of electrode potential. Since electrode potential is a thermodynamic quantity, we discuss this concept first at the well-defined state, equilibrium. And also, as equilibrium is always the destined state of a spontaneous reaction, the discussion of a substance's electrochemical properties under this state allows direct comparison between different species. So we start with equilibrium electrochemistry. Consider simple one-electron transfer electrochemical equilibrium established at a single electrode solution interface. This is solution, this is the electrode, this is the solution, and this is the interface. O and R here in the equation are the redox couple species in the aqueous solution. Z and Z minus 1 are their charge numbers respectively. And E minus brackets M is the electron present in the surface of a solid electrode, which is usually a metal. Then we focus on the electron transfer process during the establishment of this equilibrium. So we need to resort to the Gibbs energy curve we discussed in last section, which is Gibbs energy of the system plotted as a function of extent of the reaction, and the Gibbs energy curve would look like this. And the lowest point here is the equilibrium state. Then we consider two processes. First, the initial state lies to the left to the equilibrium. So to reach the equilibrium, the forward reaction needs to occur, which means electrons will transfer from electrode to the solution. And before any electron transfer, the electrode must be electrically neutral. And this is for electrode phase. And after the electron transfer, the electrode loses many electrons, and therefore the electrode must bear a positive charge. And to maintain the neutrality of the electrode solution interface, the solution side must bear a negative charge accordingly. And conversely, if the initial state of the reaction system lies to the right of the equilibrium, and the electrode phase must change from neutral to negatively charged for this second process, such that in either case, 1 or 2, there must be a charge separation developed at the electrode solution interface at equilibrium. As a result, there must exist an interfacial electrical potential difference, or we can call it interfacial potential difference. However, this quantity is unmeasurable, and therefore to make it measurable and thus meaningful, we need to let it refer to a reference level. So we define electrical potential as the interfacial potential difference under study minus another for reference. So from this relation we can see the larger the electrode potential, the bigger the interfacial potential difference, and therefore the greater extent and thus tendency of an electrochemical electron transfer for reaching the equilibrium. That's why we use electrode potential to quantify the tendency of an electron transfer. And importantly, in this section, we know that the origin of electrode potential lies essentially in the charge separation developed at the electrode solution interface. The establishment of electrode potentials we discussed last section can be precisely described in thermodynamic terms. For electrochemical systems, the introduction of electrode phase necessarily leads to the involvement of electrical energy apart from chemical energy. So the Gibbs energy of the reaction system is described in terms of electrochemical potentials, which includes electrical terms. For given species I, the electrochemical potential mu I dash equals to mu I, which is the chemical potential, plus the product of Z, F, and phi. Z here is the charge number, F is the Faraday constant, Phi is the electrical potential at the point of species I. Then consider again the same simple one electron transfer equilibrium, OZ plus electron, one electron, and RZ minus 1. Then we can describe the change in the Gibbs energy of the system equals to the sum of the product of electrochemical potentials and the change in their amounts. Then we have reaction Gibbs energy equals to mu R dash minus mu O dash minus mu E dash, which therefore equals to mu R plus Z minus 1 times F times phi S, which is the electrical potential of the solution side of the interface, minus mu O plus ZF phi S minus brackets mu E minus F phi M, and phi M is the electrical potential of the electrode side of the interface. Tidy up these terms, we have mu R minus mu O minus mu E plus F phi M minus F phi S. Then we further break down these terms as mu R standard plus RT over F ln AR over AR standard minus the same for O ln AO standard minus mu E plus F phi M minus phi S. Rearrangements gives that the reaction Gibbs energy equals to F phi M minus phi S plus delta mu standard plus RT over F ln AR over AO, where delta mu standard equals to mu R standard minus mu O standard minus mu E, and this term is actually the standard chemical potential change. So at equilibrium, we have reaction Gibbs energy equals to 0, so the interfacial potential difference equals to minus delta mu standard over F minus RT over F ln AR over AO. And apparently this is for a single electrode solution interface by which we could locate the electrochemical equilibrium, but since this quantity is unmeasurable, we need to refer it to another one developed at another electrode solution interface. So we need to have a reference electrode reaction which can be O prime plus an electron gives R prime. Then the electrode potential equals to the difference between the interfacial potential difference of study and that only for reference. So apparently we will have these terms, and if we tidy up, we would have E standard minus RT over F ln AR AO plus C, where the standard electrode potential equals to the negative difference between delta mu star over F and constant C equals to RT over F times AR prime over AO prime, which reflects the dependence of electrode potential on the activity ratio of the redox couple used in the reference electrode reaction. And if the reference electrode is standard hydrogen electrode, we have C equals to 0, and we have E equals to E standard minus RT over F times A ln AR AO. And this equation is the famous Nernst equation, which is extremely useful as first it directly links the electrode potential under any experimental condition to those under standard condition. The standard condition is a bit different from general chemistry, which is 25 degree, 1 atmospheric pressure, and 1 molar for all soluble species. Second, from this equation we could see that the establishment of this equilibrium gives a certain electrode potential. So we can say conversely that if we apply a fixed electrode potential, then the equilibrium of the reaction system will be determined, and so will the tendency for the electron transfer. Having understood the origin of electrode potentials both chemically and mathematically, we then discuss electrochemical thermodynamics simply based on electrode potentials. Consider again the simple one-electron transfer equilibrium between O and R redox species. And then we have reaction Gibbs energy equals to minus Fe, and here importantly, E is the electrode potential in a complete cell consisting of two electrode solution interfaces, and it can be understood either as the difference between the interfacial potential difference of study and that for reference, as we discussed in last section, or the difference between half reaction of reduction and oxidation in a galvanic cell. Similarly, we consider three cases. First, if E is positive, then the delta G is negative, so that the forward reaction of the reduction of O would occur. And second, if E is smaller than 0, the reaction Gibbs energy is bigger than 0, so the backward process of the oxidation of R would occur. And third, if E is equal to 0, then the reaction Gibbs energy equal to 0, so we have no net reactions and the whole system is in equilibrium. So in this sense, when we know the values of the electrode potentials under a certain experimental condition using Nernst equation, we can judge to which direction the reaction would occur, and therefore we fully understand the origin of an electrochemical electron transfer. In the end of this lecture, I'm going to present you some useful notes on distinguishing similar concepts to avoid possible confusion. The first group is electrochemical potentials, interfacial potential differences, and electrode potential. Electrochemical potential is used in fundamental electrochemistry to account for both electrical and chemical energies. So it's the analog concept to chemical potentials and has the same unit of kilojoule per mole. However, electrode potentials are much more often used in practical electrochemistry, so the discussion in the whole lecture is based on electrode potentials. And interfacial potential difference and electrode potentials are both solely electrical terms, and therefore it has the same unit of volts. The latter two concepts are pretty similar, but they should not be mixed up. To explain the difference, let's consider two electrodes. One is for study, another is for reference, and we connect the two electrodes and immerse in solution, and this level is the electrode solution interface. On the electrode side, we assume the electrical potential of this point is phi m, and this point on the solution side is phi s. And what we are interested in is interfacial potential difference established at equilibrium between these 2 points. However, this quantity is so difficult to measure because the electrical potential is defined as the work required to bring a unit point charge of 1 coulomb from infinity to the point of interest. So in reality, we made a whole lot of efforts on precisely measuring the absolute electrode potentials of a reaction system at equilibrium. For example, the absolute interfacial potential difference of a standard hydrogen electrode is measured as 4.44 plus minus 0.02 volt. And then treating this as a reference level, we measure the interfacial potential difference of any other system relative to it. So we need the electrode potential as the difference between the interfacial potential difference of a studied system and that for a reference. And formally, we use standard hydrogen electrode as a reference electrode system. And meanwhile, for convenience, we assume this value to be exactly 0 volt instead of 4.44 volt. And therefore, electrode potential is of important practical use in fundamental electrochemistry, because after all, electron transfer only occurs in a complete circuit, so it is the difference between the two interfacial potential difference that matters. The other group of similar concepts are various electrode potentials. The half electrode potential is always reported against the reference electrode, and actually this quantity is exactly what I just described, the E here. And E standard is apparently the electrode potential and the standard conditions. So far, the electrode potentials we discussed all relate to the activity of each electroactive species, which is defined as the product of activity coefficient and the concentration of species I divided by the standard concentration, which is usually 1 molar. And in many cases, especially at high ionic strengths, the two values can differ a lot. For example, when the activity of protons is 1, then the concentration should be 1.18 molar at 25 degrees C and 1 atmospheric pressure. So we can see there's 20% difference in the values. And in practical electrochemistry, we use concentrations instead of activity. So we need to define another quantity, standard formal potential, as the standard potential minus RT over F times ln a ratio of activity coefficient. As such, we can relate the electrode potentials either calculated or measured under any experimental conditions to that and the standard condition and the ratio of concentrations directly. And now I hope I have clarified the differences between various electrode potentials.